I think it's a good time to start. So for the last day, we're going to be delving into some more Bayesian X-ray analysis, but this time this is going to be from a PhD student at Geneva, working with Professor Stefano Pani. Please take it away whenever you're ready.
Yeah, great. Hello, everyone. Good afternoon. I'm Lingsong. Thank you very much for the organizers to invite me and give me this opportunity to present my PhD work about the Bayesian spatial analysis and population inference of AGN in large X-ray surveys, especially with XMM-Newton, because this is the main instrument that I've been working on. So in my talk, I will mainly focus on two parts. The first one is to talk about the spectral fitting method for spectrum of AGN in large surveys. And second is the population inference, which reconstructs the distribution of the spectral parameters using the PDFs that we obtain from the spectral fitting step. And in the end, if I still have time, I'll briefly show you our pilot study, the results of our pilot study on the XMM-COSMOS survey. So let's begin with a brief recap of X-ray emissions in AGN. So I believe you have already heard about this during this week, so I will just briefly go through it. So in this sketch, you can see the primary radiation shown in green, which is inverse Comptonized, which inverse Comptonized the UV disk photons through this X-ray source, the hot corona. And it can be absorbed if it goes through some absorbing material and give you this sort of absorbed power law here. And apart from this primary power law, you can also have secondary components like the reflection with the iron mesh line at 6.4 TeV, and also soft success, which also comes from the inner region of AGN, and the mirror scattered component of the primary power law from some ionized hot gas. And this scattered component can be important when the primary power law is highly absorbed, because in the soft part, it can sort of usually bypass the absorbing material so that it would be dominant in the soft X-ray range around or below 2 TeV. And also you can have some thermal emission from the host galaxy shown like this. So if you put all of these components together in a spec, you end up with a full model, which is rather complicated like this. And this would give us mainly two difficulties when we try to fit this the spectrum in large surveys. The first one is the conflict between this complex modeling versus the in average low data quality, which has signal to noise ratio around 3 or mostly below 5. So how do we fit the low quality data if we use a simple model or if we use a complicated model? And the second difficulty is the conflict between the complex modeling versus the large number of data. And we're talking about at least 1,000 sources. And this size of the AGN sample is growing really rapidly in recent years. So like in XXL, we have around 26,000 sources, and in the future, Eurocita would give us like millions of AGN. So we really need some very efficient way to fit all this spectrum. So for the first difficulty, despite of the very complicated X-ray spectrum model I just presented, the typical spectrum we see in large surveys would look like something like this. So this is an example from the XXL survey. And actually this one has quite decent data quality. So I believe the signal to noise ratio is around 5-ish for this guy. But still, looking at this spectrum, you would think that a simple power law could make a fairly good job. And if we, so you may wonder if we still need more complicated model to fit this one. So this is actually the first or the classic solution to this difficulty. So you can start with a simple model and only add more components when the more complicated model is preferred using sort of the C-stat or AIC or PIC, etc. However, this solution could give us quite large biases, as I will show you an example later, but in a Bayesian way. So I guess we're all here more inclined to the Bayesian solution because we're talking about DXA. So in a Bayesian way, we can apply actually the full model I just showed to all the sources regardless of the data quality. And what we should do is just to use to apply informative trials on the parameters of secondary components like reflection, soft access, and so on, which are difficult to be constrained using our data quality. And these informative trials or strong trials, we can obtain them from deep surveys like Swift path surveys, where these components can be actually constrained. So use their knowledge as our prior knowledge in our work. But for the main special parameters like the NH or photon index gamma, we apply non-informative trials because these parameters are expected to be constrained in with our data. And of course, we use multi-nets to sample from this complex parameter space in order to avoid being trapped in some local maximum. So here I'm showing you an example of the fit of a simulated sample using both the full model, which I just presented, and the very simple model, which is just an absorbed power law. So the spectrum is simulated with a full model, with actually the true NH to be relatively high, so higher than 10 to the 22 per centimeter square, with some soft access and scattering, etc. So it makes up the total spectrum to be fittable or can be well fitted using just a simple power law, as you can see on the right here. But the simple model would give you actually a very biased NH measurement, which is smaller than 10 to the 21 centimeter per square. And to give you a better view of these measurements, so on the bottom, I'm showing you the PDFs for NH and photon index, NH on the left and photon index on the right. And the red areas shows the PDFs using a simple model to fit this simulated spectrum, while the purple one are the PDFs using the full model. And the green dashed line shows the true values of NH and gamma. So as you can see, the simple model, despite that it appears to fit this spectrum quite well, if you look at the statistics, the SIGSTAT or even PIC, they are quite comparable to this measurement, this fit. But the PDFs tell you that they have the simple model would bias a lot, even the main spectral parameters like NH and gamma. So my main message here is that if you apply a simple model, it could cause serious biases, even for main spectral parameters, because actually it assumes there's no secondary emissions at all. So it's kind of equivalent to apply a very strong trials on those secondary components that force them to be zero, which is not true. So for the second difficulty, which is the conflict between the complex modeling and the large number of data, the large number of parameters and the fact that we have to model the source and background jointly, and also we have to convolve the aspect model with RMF at each sampling step if we are using a spec. It will be very time consuming. So as the first year of my PhD, I spent like 20 hours for fitting each source. So it's really not practical if we have a very large number of sources. So our approach to treat this difficulty is to actually extract spectra in a fixed energy band. So around 10 bands also, so that the RMF can be identical for each source, for every source in our data sample, so that we can tabulate the expect models by pre-convolving the models with the RMF. And in the real fitting sampling step, we can simply use pure Python codes to interpolate between the stable grids to obtain our fitted spectrum. And this gives us a much faster computation speed, which only needs like 20 minutes for each source. But of course, the drawback of this method is that it forces all the data, all the spectrum to have the same energy resolution, because of which we would lose some information for bright sources. So we did also some tests to show that for bright sources, we do not lose much information. I mean, the PDFs would be broader, but we still have constraints, even if we use lower resolution data. But since we are talking about large surveys, so for most spectra, the number of things are actually comparable. So if you're interested, I have some more plots to show you, but I see I don't have much time right now. So feel free to talk with me if you're interested. So then let's move on to the second part, which I will talk about our population inference method. So now we have the PDFs of the spectral parameters from the spectral fitting step. How do we reconstruct the parent distributions based on these PDFs? The most straightforward way would be simply use the stack PDF or point estimators like medians or so. But I guess you have already heard from previous talks that the stack PDF would introduce high bias as well. And it's actually statistically meaningless because it cannot add up independent probability. And the point estimators are simply not satisfactory in our case, because the PDFs we have are mostly not very well constrained because the data quality is not that high. So we would have some loosely constrained PDF and sometimes even have some multimodality. So if you use just a simple medians, you would lose most of the information you have in the PDF. And just to give you an example, here are the reconstructed distribution using medians and stack PDF for two simulated samples. So one sample with NH around 10 to the 20, and the other with NH much higher, around 10 to the 23. So one unabsorbed and one absorbed. So as you can see for the unabsorbed sample, these two methods are terribly wrong. The medians would give you the answer that is one order higher than the truths, and the stack PDF is simply flat. While for the absorbed sample, it's much better. Still, you see the distribution extends quite a lot to the higher or lower NH. But I guess you have already noticed that the results are very different for these two samples, namely for the unabsorbed and absorbed samples. And the reason is that despite of the bias introduced by applying stack PDF or point estimators, there is also this effect of the bias in the PDFs of NH especially. So if we look at unabsorbed source, imagine that we have a source with NH around, so close to 10 to the 22, like around 10 to the 21.7 here. The PDF of this source would most probably be like this one, the Y contour. So the PDF would be kind of flat until the lower boundary of the NH parameter space. That's why the median of this PDF would simply be very close to the middle point of the unabsorbed region. And the reason for this is that when the NH becomes very small, the likelihood would be very insensitive to the change of NH. So you change NH to even smaller, the spectrum doesn't feel it. So that's why it's really difficult to constrain NH when it's when it's in the unabsorbed region. So I call this systematic bias because it's determined by the nature of the X-ray spectrum. So it's very difficult to take care of this bias. And the way we are doing it, so here I'm just showing you a real PDF of a simulated sample, simulated source, sorry. So and you have the true NH here, and the PDF is like this. So that's why if you look at the sample of the unobserved sources, the reconstructed distribution using medians would be like this. So how do we take care of this bias? So we came up with the idea of this redistribution matrix. And to understand this, maybe you can recall the RMF that I also just talked about when we fit X-ray spectral using, for example, SPEC. So the RMF is a map of the incident photon energy to the energy channels. So for example, take the Chandra, for example, if you have incident photon energy with 5 keV, it will not be one-to-one registered in the channel. It will be a distribution over several channels. And this is like a technical issue, so we can calibrate this by some ground-based experiments so that we can convert the distribution of channels to the photon energy. So similarly, if we can have some calibrated distribution matrix that map the spectrum with a given energy to the probability distribution over NH, which is simply the PDF, then we could take care of this similar behavior of the redistribution. So, but of course, in this case, it's much more complicated because for the RMF, it's only dependent on the incident of photon energy. But for NH, it's also dependent on many other spectral parameters, like NH is heavily dependent on gamma. So if we look at the PDF of single or individual sources, the PDF would probably be different, even with the same true NH. But if we think of a collection or a large sample of sources with the same NH or similar NH, like in the same NH bin, the stacked PDF of NH would be only dependent on NH itself, because the contribution from other spectral parameters would be marginalized off. So, which is similar to the marginalization of nuisance parameters when we calculate the marginalized PDF in the Bayesian inference. But yeah, so except the spectral parameters, it's also dependent on other the characteristics of the spectrum of the sources, like redshift and the signal-to-noise ratio, which I'm going to show you later. So here is the dependence of the redistribution of NH on redshift and signal-to-noise ratio. So here I'm showing you the dependence on the signal-to-noise ratio in the 4 different meaning. So of course, for so without any signal, the true NH of the sample is in this orange bin. So the stack PDF would be without any signal to recover this NH, the true NH. So with very low signal-to-noise ratio, we can see a slightly increased signal here, but it's still very difficult to recover it. And for signal-to-noise ratio above 3, we can finally have some strong signal here. So that's why, so, and for the dependence on redshift, for very low sources with very low redshift, it's much better constrained. The NH can be much better constrained compared to sources at very high redshift. And this is simply because that we are looking at the X-ray data. So if the source, the spectrum is redshift outside of the energy band we are looking at, then we don't have any information to constrain the absorption. So these are 2 very important parameters that we have to be careful when we build the redistribution matrix. So in the so when we build the redistribution matrix, we have to be careful with that the simulated sample has to be has to have a large sample size, so that in each NH binning we have enough statistics, and also we have to use a very realistic simulation method that the simulated sample and the data sample has the same selection function and the same redshift and signal noise ratio distribution, which I will show you an example later when I show you the validation of our method on some simulated sample. So the general idea of our population inference method can be summarized here. So first of all, we parameterize the parent distribution using a histogram model or a step function, and with parameter pi for each bin, and the pi naturally follows the Hitchler distribution, which constrains the sum of the pi to be 1. And then we apply this redistribution matrix on the histogram model, the parent distribution model. And then we forward fit this distribution model, redistributed parent model to the stack PDF. And then finally, we just need to implement the likelihood to this procedure. And the only ingredient missing here is the distribution of the stack PDF. And this is something problematic because, as I just said, the stack PDF is actually statistically meaningless. So we do not have any analytical form for its distribution. So we have to rely on something like Bootstrap to infer its distribution. But luckily, we find that the distribution of the stack PDF follow nicely the multivariate distribution. So the distribution of each PI is nicely a Gaussian, so that we can easily implement it in our fitting procedure. So now I will show you the validation of our method using some simulation. And since we did a pilot study on the XMM-COSMOS dataset, so we simulated a realistic sample of 10,000 Cosmos light sources, which is used not only to validate the method, but also to build the matrix. And yeah, I think I don't have time to go into very details. So here I'm just showing you that the simulated sample, which is shown in orange, is matching quite well with the Cosmos data sample. So in terms of the redshift distribution and the LX distribution. So yeah, and here I'm showing you that the signal to noise ratio distribution of the two samples also match with each other. And then I would jump in directly to the results of the simulation. So here is reconstructed NH distribution for a subsample of the total simulated sample, which has only 700 sources. And the redistribution matrix is built with the total simulated sample. So our result is shown here in black. As you can see, it nicely fit the NH distribution for the soft sources. And also for the soft sources, the arrow bars correctly shows that we do not have any constraining power when NH is in this regime, rather than the medians would give us some false peak here, and the stack PDF is simply just flat even until around 10 to the 22.7-ish. So it completely misses the valley between the two peaks. And here is the result of applying our method to infer the obscured AGN fraction, which is defined by NH above 10 to the 22, with redshift and the intrinsic X-ray luminosity. So as you can see here, the true relation is shown as the black line. And if you use stack PDF for medians, you can see you will have a very large bias for high redshift sources. And for the LX, if you use stack PDF for medians, you will totally miss the peak around here. So maybe I don't have time to go into the results of XMM-COSMOS. So just very briefly, we found 119 sources in the XMM-COSMOS survey, and most of which have spectroscopic redshift, and others have very high quality of photometric redshift. And we went through all the spectral fitting and population inference method steps and end up with the results like this. So here is the reconstructed NH distribution for this data sample. And as you can see, we have quite good agreement with previous studies. And our result kind of show that, more obviously show that there is a bimodality in the NH distribution. So the difference between the peaks are more than 2 orders of magnitude. And this kind of suggests that there are 2 absorption sources for NH. One is galactic and one is circumnuclear. But of course, you see here the selection effect is dominating. So we definitely need more data to study highly absorbed sources or competent-6 sources. And this is a result for gamma, and we did it for unabsorbed AGN and also absorbed AGN, which you can see is not that Gaussian-like, and most of the sources would have photon index around 2. And there is some hint for different distributions between absorbed and unabsorbed AGN. So like for unabsorbed AGN, it's more likely to have photon index above 2, while for absorbed AGN, it's more likely to be harder, so below 2. And this is a result for the obscure AGN fraction with the intrinsic luminosity. So it's basically consistent with previous results. But yeah, we need more statistics here at a lower luminosity range. So I'll leave my summary here. Sorry, I don't have much time for discussion, but yeah, thank you much for your attention, and I will be happy to take your questions.
Thank you very much, Lingsong, for a very nice presentation. So are there any questions in the room for Lingsong? Any at all? So I was actually wondering, so you had the full model, right, with quite a few components. I was wondering if the reflection component is the reflection fraction of free parameter.
Yes. So the only free parameter, let's go back to. So the only free parameter for the reflection component is the relative reflection. And we fix the inclination angle and link the normalization to the primary power law. Sorry, okay, now it's here.
Oh yeah, that's cool. So I was wondering, when you mentioned the bias with fitting a simple model versus the full model with, for instance, you showed that very nice plot of you get a flat photon index with unobscured versus the true obscured versus a more reasonable gamma. I was wondering, wouldn't having gamma free and the reflection fraction free also pose this problem, i.e., for this particular data quality, right? Couldn't you envisage maybe some data quality finding equally probable to have a strong reflection fraction, but correspondingly flat intrinsic photon index, or flatter than what it should be? Could that be a possibility?
So sorry, I couldn't really hear you very well.
Might be the microphone.
Yeah, it's kind of blowing.
Yeah, okay. Let me try something else. Is that better?
Now it feels a bit farther away, so your volume is a bit.
Is it? Microphone is a bit. No, so the microphone is too faint. It's too faint? Yeah.
Okay, then yes. Yeah, this one.
Okay, then maybe the microphone will be better.
Can you hear me now?
Yeah, it's much better.
Sorry about that. Yeah. So I was essentially just wondering, so there's a clear degeneracy problem here, right? That if you fit a model that's too simple, that doesn't have that doesn't have the extra reflection component, for instance, then you can end up with a flat photon index and a low column, right? Because it's just saying that it's intrinsically flat. I was wondering, couldn't you get the same issue for this particular data quality if you have, for instance, a very strong reflection fraction, but then it would not necessarily need a very strong column to compensate for the fact that you're seeing a Compton hump, right? So you would end up with a flat photon index, but just an what's the word? A bit like a slightly too strong reflection component instead.
Yeah. So in this case, you have to really dig into the details that how strong the reflection component should be. And this can be constrained with with the prior on the relatively reflection parameter. So what we have is kind of a flat prior for this parameter until like 1-ish, and have a cut or decrease above it. So we kind of constrain very strong relative reflection.
Ah, okay, very cool. Thank you.
And this is from the SwissBAD result.
Okay. Thanks. Are there any questions on Slack or on the chat? Yes, I think we have one question from Ake. Do you want to unmute and ask your question?
Yes. So thank you for the nice talk. So I was wondering, did you compare, or are you planning to compare the results on the obscuration, for example, on the samples in the GeneraCosmos, the analysis that has been already done in GeneraCosmos, so Brightman 2014, Lanzuisi 2013?
Yes or no, because of course we have compared it, but as I just presented, the results of the method is really different. So we use all the complexity of the model.
Mm-hmm.
So yeah, and the population inference method is also very different. And yeah, I mean, the comparison is quite straightforward. If you consider all the uncertainties, they're agreeable, but yeah, it's difficult to say, taking into account the uncertainties. So.
Mm-hmm. Yeah, I see. I'm just interested in the in how model dependent the column density is in general, and I guess this is one way to quantify it. Okay, so thank you.
Okay. So are there any more final questions or comments?